This lecture deals with section 8.6 on power series. So let's start with a definition. What is a power series? Power series centered at x equals c is of the form sigma n goes from 0 to infinity a sub n times x minus c to the n. Okay, so you can see here that we have a series coupled with a term involving x. So a power series is a function of x. A power series is a function x. And it may converge for various choices for x. And note, if c equals 0, then we call the power series let's hold off on that. Okay. So what's the motivation behind this? We're going to be dealing with a particular type of power series next lecture, but we're going to try to do a little bit of analysis with these things to see how they converge or not. Okay, so let's do an example. Right, the first 4 terms of the power series. A sigma goes from n goes from 0 to infinity of x to the n. So the first 4 terms, the first term is when n is 0. So when n is 0, this would be x to the 0 power plus n is 1, x to the first, and when n is 2, x squared, and when n is 3, x to the third. Or 1 plus x squared plus x cubed. Okay. So you can see that we can continue this actually. So you get this infinitely long polynomial function that is the series there. How about this one? N goes from 1 to infinity, negative 1 to the n plus 1 times x plus 1 to the n over n. So our first 4 terms would be, now carefully plug in n's here, so if n is 1, this would be n plus 1, 1 plus 1, which is 2, and negative 1 to the second power is positive 1. Here we get x plus 1 to the first power over 1. Plus the second term would be n is 2, so n 2 plus 1 is 3, so that would be actually a negative 1, so we can put a negative there, minus n is 2 still, so x plus 1 squared over 2. Next term is when n is 3, so we would get a 4 here, that would be a positive 1. X plus 1 to the third over 3. And the last one, the fourth term here would be n is 4. This would give us an odd power, so we get minus x plus 1 to the fourth over 4, and so on. Right? So here we have the first 4 terms of that power series. last one, n equals 0 to infinity, -1 to the n plus 1, x minus pi to the 2n over 2n factorial. So the first four terms, if n is 0, we get -1 to the first, which is -1. N is 0 here, so that would be x minus pi to the 0, which is also just 1, over, if n is 0, we get 0 factorial, and 0 factorial is defined to be 1. If n is 1, we get a -1 squared here, so that'll be positive. If n is 1, we get second power over 2 factorial. Of course, we'll have some alternation when n is 2. If n is 2 here, we get to the fourth power over 4 factorial. And then lastly, plus n is 0, 1, 2, 3 this time, so a positive x minus pi to the 6th over 6 factorial. Okay. So our motivation is when do these things converge, right? When do these power series converge? That is, for what x? For what x's does the series converge? So we can take a look at Desmos to see kind of an investigation with this. So let's consider the first series. So our first series from that first example is n goes from 0 to infinity. So let's put let's say n. Well, let's just put in a big number, say 1,000, x to the n. Okay. So you can see here, this is the function that we're dealing with for various values of x. It's going to run through 0 to 1,000 and calculate the sum given the specific value of x. So when x is 0, here, when x is 0, the sum will be equal to 1. When x is -1/2, looks like the sum is around 0.6, and so on and so forth. So you can see here that we have convergence on a big portion of this curve here. And then you can see at some point, at maybe, let's say, -1 here, you can see the value of the sum increases nearly vertically, right? So you can see that we have convergence on a particular interval, right? So from -1 until it looks like +1, we will have convergence of the series. So depending upon the value of x, the series will converge. And anything outside that interval will have divergence here. So you can see it diverges when x is -1, and it diverges after x is +1, right? So here we still have a finite value, but as we approach 1, you can see the sum is growing, right? So we can see that the convergence happens on a particular interval. So let's write that in our notes. We can see that the convergence depends on x, and the convergence happens on an interval. Okay. So here's a theorem. Let sigma n goes from 0 to infinity, a n x minus c to the n be given. Then one of the following is true. 1, the series converges only at C. 2, the series that, let's say x equals C here, at x equals C, the series diverges for all x. Or 3, the series converges on an interval. Some interval, say C minus R to C plus R, where R greater than 0 is called radius of convergence. Radius of convergence. Okay. So, note, if the series converges only at C, then R is 0. And if it converges on negative infinity to infinity, then R is infinity. Okay. And we call the radius of convergence, excuse me, the interval of convergence, is the set of all x's such that the series converges. Okay. So this interval C minus R to C plus R, that's our interval of convergence. And it is all the list of all the values for which the series converges. Okay. So determining convergence of a power series. So how do we do this without the aid of a calculator here? Okay. To do this, we use a modification of the ratio test called the absolute ratio test. Okay. So it's basically just the ratio test of the absolute value of the series. Okay. So we perform the ratio test on the absolute value of the terms in the series. Okay. So let's take a look at how we do that. So we want to determine the interval of convergence for the series, power series. So let's start with that example. N equals 0 to infinity with x to the n. All right, so to perform the absolute ratio test, what we do is just take the ratio of the n plus 1 and n terms and the absolute value of those. So we look at, so we consider the limit as n goes to infinity of the absolute value of an plus 1 x to the n plus 1 over an x to the n. Okay. So this is basically just our ratio test. Recall that we look at the ratio of the an plus 1 if we're just doing a regular series. We look at this ratio without the absolute value. Of course, here we're just going to look at the next term in the series divided by the previous term and hope that limit goes to some finite value that's less than 1, right? We want to consider this and ask ourselves, is this limit less than 1? Or for what values of x make this limit less than 1? Okay, so let's look. So for a particular series that we have here, we'd be looking at x to the n plus 1 over x to the n, absolute value of that. So again, the next term in the series divided by the previous term, and we're looking at that limit as n goes to infinity. So what is this? This is the limit as n goes to infinity. We can cancel here, so x to the n's cancel with x to the n's here, leaving us with just the absolute value of x. Okay. Now notice that this term here does not depend on n, so this is simply, we treat it as a constant, basically. This is equal to the absolute value of x. Now this won't always happen, right, because we might have some terms involving n here, but this is a simple one. So then we ask ourselves, for what values of x is this less than 1? Well, the absolute value of x is less than 1. What does that mean? Well, that means that this can be any number in between -1 and 1. Okay. So we know that the power series here will converge for all values of x that are in between -1 and 1. That's what we saw from Desmos, right? Get back. So here was our series, right? So we can see that for all the values of x in between -1 and 1, we'll have convergence. The sum is some finite value, right? So the only question is, what happens at -1 and what happens at +1? Does it converge for those values of x, right? So anywhere outside of this region, we know it diverges. The sum will be infinite. So we need to check to see whether it converges at these endpoints of this interval, okay? So from here, we can gather that the radius of convergence, we know that the radius of convergence is 1, okay? It's 1 because this guy's centered at 0, right? Because we don't have an x minus c term. We're centered at 0. And the interval is 1 unit across from the center outward. So we know the radius of convergence is 1. But what we want to do is test to see if we have convergence at -1 and convergence at +1. So let's do that. So here we test to see if the power series converges at x equals -1 and x equals 1. So how do we do that? Well, we just go back to the original series and look at that, right? So if x were equal to -1, this series would be if x equals -1, power series becomes sigma n goes from 0 to infinity, -1 to the n. So this is a specific series that we can test the convergence on. So it looks like, to me, this is going to oscillate in between -1 and 1. The terms of the series go back and forth between -1 and 1. So I'm thinking divergence here. So let's use the nth term test to see whether this guy converges. Recall that the nth term test says that if this the limit of the terms of the sequence don't go to 0, then we have divergence, right? So test this limit, -1 to the n. Well, what's this limit? This limit for various values of n oscillates back and forth between positive and -1. So this limit does not exist, which implies divergence, right? So this diverges by the nth term test. So we do not have convergence when x is -1. If x is +1, power series is sigma n equals 0 to infinity, 1 to the n. And you can see here that this is just the sum of 1 plus 1 plus 1 plus 1 plus 1. I can use the nth term test again. Limit as n goes to infinity of 1 to the n. Well, this is equal to 1. Diverges as well. Okay. So our interval of convergence is for when x is in between -1 and 1, and our radius of convergence, of course, is 1. Let's try another. About this one, n goes from 0 to infinity of x to the n over n factorial. Right, so let's perform our absolute ratio test. So we're going to use absolute ratio test. Again, here basically what we're doing is testing for absolute convergence along the interval. So we want to consider the limit as n goes to infinity of the ratio of the next term with the previous term, all absolute value. So that would be x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. So let's see what we get. Limit as n goes to infinity, absolute, x to the n plus 1 over n plus 1 factorial times the reciprocal of this guy, n factorial over x to the n. All right, so we have some cancellation here. X to the n plus 1, all n factors of x cancel with all n factors of x there. Let's get our limit. N goes to infinity. We'll have an x left at the top. And here, if we were to expand these, this would be n plus 1 times n minus 1, and so on. This guy is n times n minus 1, and so on. So you can see how the cancellation happens here. N minus 1, cancel n minus 1, and so forth. So we're left with just n plus 1 at the bottom. Absolute value. Now, let's take a look at this. Notice that all the n's in our original series, all the n's are positive, right? So this number at the bottom is always a positive number. So actually, I can rewrite this limit in a different way. Limit as n goes to infinity. I'm going to put out the 1 over n plus 1 times the absolute value of x. This is doable because the bottom number is always positive, because our n's are always going to make something down there that's positive. Okay? So notice that this guy does not depend on n, so I can actually pull this out of the limit. But this one does depend on n. Okay? So what's this limit? The limit as n approaches infinity is 1 over n plus 1 is 0. So this limit is 0, so that knocks everything out, right? Regardless of the value of x, this limit is always going to be 0. So what does that mean? Well, we know, so for what values of x is this limit less than 1? Well, that's all values of x, right? Because the limit's always 0. It doesn't depend on the value of x here. So here, our interval of convergence is negative infinity to positive infinity for all values of x, right? And the radius, of course, r is equal to infinity. So it doesn't matter. Value of x here does not matter. You always get a sum that is finite. So let's see if we can look at that on Desmos. So you can see here that for all values of x here, we never get something that's infinite. This guy just continues on for all values of x. It's going to be a big number, but it's going to be a finite value here, okay? Let's try another. How about n goes from 1 to infinity of negative 1 to the n plus 1 x to the n over n. Let's look at our absolute ratio test. Again, we want the quotient of the next term with the previous term, all absolute valued. We take a limit. Limit n goes to infinity. Absolute. The next term would be negative 1 to the n plus 1 plus 1 x to the n plus 1 over n plus 1 times the reciprocal of this guy, so n over negative 1 to the n plus 1 x to the n. So we have our limit. Let's see what cancels. So these negative ones will cancel with all of those, leaving us with a negative 1. Let's see, all of our x to the n's cancel with all n of those, so we'll have an x left at the top. And then we have n over n plus 1, which does not cancel. Okay. All right, so let's see how we can write this. So the absolute value is going to kill that negative 1, so that's gone. We still need our absolute value of x, because x can be positive or negative. And then this guy is always positive, so we can pull him out of the the absolute values there. So what we'll have is the limit as n goes to infinity of the absolute value of x times n over n plus 1. Once again, that negative 1 is killed by the absolute values. We still need the absolute value of x because x can be a positive or negative value. And the n's are always positive, so this guy is always positive. We can pull him out of the absolute value. Now, rewriting this, because this guy is not dependent upon x, let's pull it out. So the absolute value of x times that limit. And what is that limit worth? Well, the powers are the same, so it's just the ratio of the lead coefficient, so this is just 1. So that is absolute value of x. Okay. Again, this is 1. So, at the moment, our interval of, we want to, again, by the ratio test, we want this quantity to be less than or equal to 1. So for what values of x is this less than, strictly less than 1, not equal to, right? If it's equal to, then it's inconclusive. So we ask ourselves, for what value of x is this less than 1? Well, x would have to be in between negative 1 and 1, right? So we need to check our, so this tells us that the radius of convergence r is 1, right? Because it's 1 unit away in either direction. This is not always the case, as we have seen. But we also, for the interval of convergence, we need to see if it converges at negative 1 or at positive 1. So we need to check that. If x is negative 1, we get this power series, the original power series is sigma n goes from 1 to infinity, negative 1 to the n plus 1 times negative 1 to the n over n. All right, so we simplify here. We have n plus 1 powers of n and n powers of n here. So this is sigma n goes from 1 to infinity of, now we just add those powers. So it's negative 1 to the 2n plus 1 over n. So let's see about this series. Does this series converge or diverge? Well, let's take a look. Notice that if we were to write out some terms of this series, note what we would get. We would get, well, if n is 1, we would get negative 1 to the 3rd power over 1, so that would be negative 1. If n is 2, we get negative 1 to the 5th power over 2, so that would be negative 1/2, and so on and so forth, right? So the top value here is always a negative 1 because of the power, right? This is always an odd number. So this can actually be rewritten as just negative 1 to the n. Negative 1 over n, excuse me. Negative 1 over n, because this 2n plus 1 is always an odd number for every n. Therefore, we'll always get this guy. So this is equivalent. And we can see here that this guy is going to diverge, right? This is actually equivalent to the negative of the harmonic series, which we've seen over and over again, to diverge. Diverges. Now we need to check at x equals positive 1. If x is positive 1, the power series is sigma n goes from 1 to infinity, negative 1 to the n plus 1, times, now we would have 1 to the n over n. 1 to the n is always 1, so we get sigma negative 1 to the n plus 1 over n. Now if we take a look here, notice that this is a little different. Now we do have alternation, right? When n is 1, we get to the square, so that'll be positive. When n is 2, we'll get a third power, so that'll be negative. This is the alternating harmonic series. We've already seen that this converges. Converges, it's the alternating harmonic series. Right? This is just the opposite of the harmonic series. Therefore, the interval of convergence is x in between negative 1 and 1, but it diverges at negative 1. It converges at positive 1, so we put an equal to symbol at 1 here. So it is convergent when x is equal to 1 as well. Okay? Let's look at this one. N goes from 0 to infinity. 2 to the n times x minus 3 to the n. Okay. So let's apply the absolute ratio test. So it's always the next term, the n plus 1 evaluation divided by the previous, right? So let's get the limit as n goes to infinity. The absolute value of 2 to the n plus 1 times x minus 3 to the n plus 1 over 2 to the n times x minus 3 to the n. All absolute value. Let's check our cancellation. Limit n goes to infinity of 2 to the n plus 1 cancels here, all of those cancel, all of those, so we left with one factor of 2. Times, same thing happens here, so all n factors of x minus 3 cancel with n of those, leaving us with an x minus 3. Okay. So notice that this limit is not dependent upon n, so that's exactly what it's equal to. So the absolute value of 2 times x minus 3 here. So by the ratio test, we know that this will converge if it is less than 1. So we need to figure out the values of x that make this less than 1. Okay. So, recall how we solve this absolute value inequality is that the values in here must be in between negative 1 and positive 1. So, 2x minus 3 less than 1. Okay. And then we just solve this. So let's divide by 2 on all three sides. Negative 1/2 is less than x minus 3, which is less than positive 1/2. Then we add 3 to all three sides, so this would be 2.5 less than x less than 3.5. Okay. So we can gather the radius of convergence here. The radius of convergence is 1/2, right? So how do I know that? Well, let's think about it. Where was this power series centered? So notice this time we have an x minus 3. It's centered at 3. So the center of this guy is at 3, and it takes a half to get to either of those. You can also get this by just finding half the difference of these guys here. So r is equal to 3.5 minus 2.5 over 2. That would be 1 over 2. You can do it that way too. Okay. So what we need to do is look at the endpoints of the interval to see if we have convergence there. Okay. So if x is 3, we can do 2.5 or 3.5 first. So let's do 3.5. If x is 3.5, then our power series, our original power series, would be n goes from 0 to infinity, 2 to the n, times 3.5 minus 3 to the n. Let's see about this. This is 2 to the n. 3.5 minus 3, that's a half. That's a half to the n. All right. Because these are the same power, we can just multiply the insides, raise it to that power. So this is like 2 times 1/2 all to the n. And this is 1. Of course, this diverges, right? Diverges by nth term test. The limit of 1 is 1, not 0. So we do not have convergence when x is equal to 3.5, but right before it, it'll converge. Okay. Check for 2.5. If x is 2.5, then sigma n goes from 0 to infinity of 2 to the n, 2.5 minus 3 to the n. What's this? That's 2 to the n times, now this will be negative 1/2 to the n, multiplying in because we have the same power, gives negative 1 to the n. And if we check this limit, the limit as n goes to infinity of negative 1 to the n just bounces back and forth between negative 1 and 1. So we know that this diverges also. Diverges by nth term test. Notice that I am referencing the test that I am using. It's important to do that. You can't just say diverges. This is the reason why, right? We have checked the limit as n goes to infinity. In this case, it's non-zero. In this case, it is non-existent, so we have divergence in both cases. Therefore, the interval of convergence is 2.5 to 3.5. Okay. 2.5 to 3.5. It does not converge at either of those values. Let's do one last one. N goes from 0 to infinity of n factorial times x to the n. Okay. So let's check our absolute ratio test. Limit n goes to infinity absolute value of the next term, n plus 1 factorial x to the n plus 1 over n factorial x to the n. Right, so we'll have some cancellation. Remember, this is n plus 1 times n minus 1. This is n times n minus 1. So this cancels out all the factorial stuff. So we'll be left with n absolute n plus 1 times x. These n factors cancel with those n. And again, n plus 1 is always positive, so we can pull him out. And since x, the absolute value of x does not depend on n, we can remove him from the limit. N goes to infinity of n plus 1. Okay, so we know that this limit goes to infinity. This is approaching infinity. Right? This limit approaches infinity. So the only thing, this is going to infinity. So the only value of x that makes this less than 1 is what? 0, right? So power series converges at x equals 0 only. So the radius of convergence is 0. Of course, there's no interval because we just have one value, that convergence here. Okay. All right, so you should be able to do your suggested homework